Chapter 2, Operations and Expressions. In this video, I'm going to cover quick versions of sections 2.1 through 2.5. These sections are a review of things that you would have seen in a pre-algebra course. So I'll cover a little bit of the review material, and then I'm going to focus on applications that this book shows that might be different than what you saw before in those courses. If you find any of these reviews a little too quick, then you can find the full versions of the lecture that I did on these from previous versions of the course. If you wanted to, for example, see 2.1, you would go to YouTube and search for Math 53, Chapter 2, Section 1, and then you could do similar for any of the other sections that you come across. You don't need to do that unless you feel like what you're getting here isn't enough and you need a little bit more review. Another thing related to that is because these are coming from some old chapters, there will be some points where I pulled some of the old video from those full sections, so you might see some page numbers don't match. Don't be concerned with that. The content that you need should all be there. All right, let's go ahead and jump in. First example is evaluate the expression 30 plus x for x equals 6. When we're asked to evaluate an expression for a certain value, all we are really being asked to do is plug that in and simplify. So instead of 30 plus x, we're going to do 30 plus 6. So we're substituting this 6 in for that x, and then we just simplify, so 30 plus 6 is 36. So anytime they ask you to evaluate, that's what they're looking for you to do. All right, let's move on to another one, more of an application this time. The enrollment fee for a college student is $87 per unit, or per hour. So complete the table below to help find an expression that describes the total cost of enrolling in n hours of class. All right, so if the student was just going to take 1 hour or 1 unit, then since it's $87 per unit, they would just pay $87. If they were going to do $2 per unit, then they would have to pay that twice, so it would be 2 times 87. If it was 3, it would be 3 times 87. If it was 4 units, it would be 4 times 87. And we'll work these out in a moment, but I just wanted to show you with the multiplication, because that helps fill in the expression. If it was n hours, then it would be n times 87. All right, and then let's bring in the calculator and calculate those out. So 2 times 87 is 174. 3 times 87 is 261. And 4 times 87 is 348. Sometimes in my math lab they ask you to enter an unsimplified expression. If they ask you to do that, you would be putting the parts like 2 times 87, 3 times 87. Sometimes they want the answer. Then you'd be putting the 174, 261, and 348. The main goal of a table like this is to help us get to that expression. And then once we have that expression, we can answer questions like the follow-up here. Evaluate the expression that you found in part A for n equals 15. So then I would just plug in the 15 in place of that n. So instead of n times 87, it becomes 15 times 87. We can bring the calculator back in one more time, do that multiplication, and we see that it's $1,305. And I would put units on this just to remind me of what this represents, that if the student were to take 15 units, it would cost $1,305. We definitely want to focus on interpreting our numbers and thinking about what they mean in terms of the applications we're working in. All right, let's move on to another one. If T is the total cost in dollars for n students to go on a ski trip, then capital T divided by little n is the cost per student. Evaluate T divided by n for T equals 9,000 and n equals 20, and then think about what does your result mean in terms of the situation. All right, so evaluate T divided by n for T equals 9,000 and n equals 20. So we already said that just means plug these in. So in place of the capital T, we would put 9,000. And I'm going to put the units on there to help me think about what it means. So 9,000, whoops, is it dollars? Yeah, $9,000, and n equals 20. So divided by n, so divided by or over 20, and then 20 what? 20 is the number of students, so 20 students. And then we can just do the division on the calculator. So 9,000 divided by 20 is 450. But because we have the units on there, we can think about what that means. $450 per student. So I've kind of done both here. I've evaluated the expression and I've thought about what it means. So I guess since they specifically asked us what does it mean, we should write a sentence. So the trip costs is $450 per student. All right, moving on to a quick review of section 2.2, operations with fractions. They want us to simplify each of the following. We simplify fractions by reducing common factors. So we want to think of what is the largest number that 18 and 30 have in common. The largest one I can think about would be a 6. So 18 is 6 times 3, and 30 is 6 times 5. But 6 over 6 is 1, so having that in there as a multiplier doesn't affect anything. 1 times anything is that thing. So when you get a factor that's the same top and bottom, you can reduce it or simplify that out, divide it out, we often say. So we end up with 3/5. And then just doing that one more time, 49 over 63, it might be a little hard to think of what these two numbers have in common at first. So just think about one of them and how it can be factored. 49 is 7 times 7, and then hopefully 7 will be a factor at the bottom also. So maybe you can do that in your head, or you could do 63 divided by 7 and see that it goes in 9 times. So 63 is 7 times 9. And then we have this common factor of 7, so we can cancel this 7 with either of those. So let's do the first one, and then we are left with 7 over 9. So when you are asked to simplify a fraction, they're really asking you to reduce it by dividing out common factors. I think it's a good practice to show that common factor before you cancel it, though that is not absolutely necessary. A lot of times people will take a number like 1830 and they will think about the 6 and they will just say 6 goes into 18 3 times and 6 goes into 35 times, so the leftover pieces are 3/5. That is also valid, but it's just a little harder for people to be able to follow. So it's just kind of a messy looking thing here. People can see what it is that we reduced or divided out. So either one is okay with me, though this one it makes it a little easier for me to give you partial credit if something were to go wrong. All right, let's look at some other examples. Perform each of the indicated operations. So we're going to look at multiplication, division, subtraction, and addition with fractions. So when you are multiplying fractions, you multiply straight across, which is to say you multiply the numerators and you multiply the denominators. Though I think it's kind of a bad idea to actually multiply it all the way out and say 24 over 63, because then it's harder to reduce. If you leave it this way, you can think about what some common factors are. Like, for example, 6 and 9 have a 3 in common. So 6 is 2 times 3, and then we already had that 4. And then the 7 is prime, so I can just copy that, and 9 is 3 times 3. So now I can cancel a 3. You can also think about if there's any common factors remaining, but on top it's just a 2, 2 more 2's, and there's no 2's in the bottom. So now I'll multiply the leftovers, which would be 2 times 4 is 8, and 7 times 3 is 21. So if you're like me, you've always heard that to multiply fractions, you multiply straight across. What that really means is that we went from 2 fractions to 1 like this. What you don't want to do is immediately multiply the numbers to get a bigger number that's harder to reduce. So you could also consider going straight from here to here, which is to think about that 3 that's in common and show it as you make one fraction. There's other options as well. People often take 6/7 times 4/9 and then think about common factors and just do the slash method. 3 goes into here twice, into there 3 times, and the leftovers give you 8 over 21. That's appealing because it's faster to do, but you're not really showing your work as well. It's harder to get partial credit. If something goes wrong, it's harder for other people to follow along. So I like this a little better, but I would accept that too. Again, though, if you messed up, it might be harder to give you partial credit. All right, how do you divide fractions? So you multiply by the reciprocal is the phrase that most people know. So you take the first fraction and you leave it alone. You change the division to multiplication by the reciprocal of what we were dividing by, or the divisor. So the one on the left is left alone, the one on the right is the right one to flip. And then as I go to multiply these together, I'm going to think about what I could do for reducing. 4 goes into 8 twice. So I'm going to write 5 times 4 on the top, and for the 8 I'm going to write 4 times 2, so that common factor is being revealed, and then just copy over the 3, cancel the 4's, multiply out the leftovers, so just a 5 on top, and 2 times 3 is 6 on the bottom, so there's my 5/6. Moving on to a subtraction of fractions. With addition or subtraction, if you already have a common denominator, then you just keep that and you do the subtraction of the numerators, so 13 minus 5. And 13 minus 5 is 8, so I have 8/18. They have a 2 in common. 8 is 2 times 4, and 18 is 2 times 9. So that revealed 2 could be canceled, and I'm left with just 4/9. Just a quick note on why it is that you keep the same denominator here. The denominator of a fraction tells you what size pieces that say the circle or square or pi has been cut into, and so this tells you what type of fraction you have, and the numerator tells you how many pieces you have. So you have 13 pieces that are each 1/18. You have 5 pieces here that are each 1/18. And when you think about subtracting things, you subtract how many you have, but it doesn't change what type you have. So for example, if you had 13 chairs minus 5 chairs, the answer would be 8 chairs. So you would change how many you have. You would do that subtraction just considering how many pieces, but you wouldn't change what type they are. So it's the same thing with fractions. You can't add or subtract them unless they're the same type. But once they are the same type, you keep that type and just do the addition and subtraction on the count. So let's think about that on this next one as well. We have 3/8 plus 1/6. So the problem here is these aren't the same type. So you want to make them the same type by making them have the same denominator. So you try and think of a number that's bigger than 8 and 6. Well, really what you're thinking of is what's the smallest number that's divisible by 8 and 6. Often it's bigger, not always. So the smallest number I can think of that's divisible by 8 and 6 is 24. 8 goes into 24 and 6 goes into 24. So what I want to do is make each of these fractions be 24ths. So to do that, it's kind of the opposite of the canceling we've been doing. Instead of canceling out a factor, you bring one in. So what factor would I have to multiply 8 by to get 24? That would be a 3. But just like if you're going to cancel something, it has to be top and bottom. If you're going to multiply something new in, you have to do that on the top and bottom also. So that way you're multiplying by 1, not really changing the value, just making it look different. And then you have plus the 1/6, but you want that to be 24ths also. So if I multiply the bottom by 4, that would make a 24. So I'll multiply the top by 4 also, so that I'm really multiplying by 1. And when I do that, now these become the same type because they have the same denominator, 9/24 plus 4/24. And now because they're the same type, I can add them by adding the counts. So the numerators, 9 plus 4/24, which is 13/24. And then just one final piece here. When you're working in my math lab, some of the problems will tell you to check your work using a calculator. That's not something that I would require of you on a test or something, but I do want to show you how to do it. You would just take the original fractions problem that they gave you. So 3/8, just use division, plus 1/6, and then you see what the decimal is. And then you take your answer and you just do the division there, and if you get the same decimal, that shows you that you've got an equivalent fraction. So it's still, if you forgot to reduce, you wouldn't be able to check that there, you wouldn't be able to tell, but it does at least make sure that your answer is equivalent to the starting point. All right, let's go ahead and look at some summaries of the different operations we did on the previous pages. So if you're multiplying fractions, this is saying if you're doing a over b times c over d, just make that ac over bd, which is saying multiply the numerators, multiply the denominators. So in words, if you're going to multiply two fractions, just write the numerators as a product and write the denominators as a product. Notice they're saying write it as a product, right? Not figure out the product. Don't carry out the multiplication, but just write them as a dot c, b dot d. And the other note I would add here is try to reveal common factors when you do that. So as you're getting ready to go from this step to this step, be looking at the numerators and denominators and think about, is there any common factor I can cancel? And if so, try and reveal that so people can see clearly where your canceling is coming from. When you're dividing fractions, it's A over B divided by C over D. We're going to multiply by the reciprocal of the divisor. So the one on the right will be the reciprocal, the one on the left will be left alone. And then when you're adding, you have to have a common denominator, and if you do, you can just add the numerators or subtract the numerators if it's subtraction, same idea, but you have to have a common denominator. If you don't, you have to follow the process from the previous page, one of those two processes, to come up with a common denominator. All right, so let's look at something a little different here, which is some properties of zero. So we need to remember that if 0 is in a fraction, is it a problem? Is it no problem? What do we do? So if you have 0 divided by 621, if you have 0 on top and then some non-zero on the bottom, then the answer to that is 0. Think about if you had no money and 621 people, then you're taking all that no money and dividing it equally, everybody gets no money. Whereas if you had $713 and no people, that's a confusing thing to think about what each person gets if there's not any people. So we end up saying this one is undefined. And essentially, that's just where it's supposed to stop. That if you are seeing a 0 in the numerator and a constant that's not 0, a constant in the denominator that's not 0, then the answer is 0. But anytime there's a 0 on the bottom, it's undefined. So they have that summary here. The fraction a over b is undefined if b equals 0. So no 0 denominators. If so, it's undefined. I just kind of want to show you why. So let me take another fraction, let's say 18 divided by 3, and think about what's the answer. It's 6, right? And then how do you check that? We would often say because 3 times 6 equals 18. That's fairly common that people would think about it that way to make sure they had done it right. So what if we had 0 over 3? So what's the answer? Well, according to this, it would be 0. And then if you check it, you would do the denominator 3 times your answer 0 and think about, is that equal to the numerator 0? And yeah, it is. So that one seems to make sense. What about this one right here? So what if you took 713 and you divide it by 0? What's the answer? Would say you thought the answer was 0. Well, 0 times 0, 713? No. And then what if you thought, well, there has to be some answer. In fact, I kind of made an x there. Let's make it a better x. What is, maybe I just don't know the answer, right? So let's throw a variable in that spot. What would that have to be? Well, it would have to be the case that the denominator times that x was equal to 713, and 0 times anything is 0. So there's nothing you could put there that would give you that answer. So there's no defined number such that 0 times that number is 713. So that's where that idea comes from. And the same thing is true if it's 0 over 0. That's a little bit of a weird case, but anytime there's a 0 in the denominator, we say that's an undefined case. All right, moving on to a quick review of section 2.3, adding real numbers. And what they're really talking about here is adding numbers when you have negatives involved. So if you have two negatives added together, then what you want to do is kind of think about, since these have the same sign, they're going in the same direction. It's like if you were on the number line and you started at 0 and then somebody said -3, you'd be left 3. And then somebody adds -2, so it's like you're moving 2 more spots over. So where would you be now? -1, 2, 3 is where you were, and now -4, 5. So this would be our answer. So to get that just without the number line, you'd say, okay, these have the same sign, so they're moving in the same direction. So I'm going to end up on the left. And how far am I going to go? 3 to the left plus 2 to the left is 5 to the left, and that negative represents that left. So when you're adding two numbers that have the same sign, essentially what you do is you just ignore that sign for a moment and think of it as a 3 and a 2. Add those together to get 5, and then you keep the common sign. And that's right here in this box. So if two numbers have the same sign, add their absolute values. So when they say that, they're saying just kind of strip away the sign and just add the numbers themselves. And the sign of your answer is the same as what the original numbers were. All right, but what if it's different? What if it's 4 plus -7? Okay, so now you're on the number line. You start out at 4 positive, so you're over here on the right. somebody says add a -7, so essentially you're adding a move of 7 to the left. So from 4, 1, 2, 3, 4, 5, 6, 7 to the left, and that ends up being 3 notches to the left of 0. So the answer there would be -3. And then how can you think of that in terms of the mechanics of it? Well, the 3 is the difference between 7 and 4 if you ignore the signs, and then the answer had the sign of the bigger of the two numbers. So we have a summary of that down here too. If you're adding two numbers with different signs, find the absolute value, which essentially means ignore the signs, just think about the numbers themselves. Subtract the smaller one from the larger one, so 7 minus 4 is 3. And then the sum of the original numbers has the same sign, so the sum is the answer, has the same sign as the original number with the larger absolute value. So of those two numbers, if you ignore signs, which one is bigger? 7. So whatever sign that has wins, and so it's a -3. So let's think about that now with these two without using the number line. These have opposite signs, so I'm going to do a subtraction, bigger one minus the smaller one, and the sign of the bigger one will win. Well, the bigger number is 17 and it's positive, so I'm going to get a positive answer to whatever 17 minus 14 is. So I just get +3 or just a 3, no reason to write the positive sign. Alright, so the same thing here. These are both negative. So according to this rule right here, the answer will be negative. And what I want to do is just ignore the signs and add 2/3 and 5/6 together. And then the reason I left a little space, and I should have done that twice, is so that I could multiply to make a common denominator. Actually, I guess I'm okay here. What's the smallest number that both 3 and 6 divide into evenly? And the answer to that is 6. So this one's already good. And if I multiplied this one top and bottom by 2, I would get a 6 on the bottom here, just like I have over there. And then just copy this negative, because that's going to be part of my answer eventually. I have 6's on the bottom, and I have from this one a 4, and from this one a 5. And then that negative I'll copy again. 4 plus 5 is 9 over 6. And because I'm running out of space, I guess I'll use the slasher version of canceling here. 3 goes into this one 3 times and into there twice. Be a little better if I showed the 3 O's canceling. And then I end up with -3/2. Alright, so there's a few examples of adding numbers that have negatives involved, and then we have these summary rules for how that works. Let's just look at a quick application now. A person bounces several checks and is charged service fees such that the balance of the checking account is negative $112.50. If the person then deposits $170, what's their balance now? So we're starting off with negative $112.50, and then we're making a deposit, so we're adding to our account $170. So what's the math going to look like on this? Well, you have opposite signs, so you're going to subtract the bigger number minus the smaller one, and the sign will be whichever was bigger. And fortunately for us in our banking situation, our deposit is bigger than our debt there, so we're going to end up in the positive side of things. And then to figure out what it is, you could do a calculator, or I'll just do it by hand here real quick. So 170.00 minus 112.50. Going to have to do some borrowing from these $70. I'll borrow 1, which will make it 69. So this becomes a 10. So the 0 minus 0 is 0. 10 minus 5 is 5. 9 minus 2 is 7. 6 minus 1 is 5. And the 1 minus 1 cancels off. So it looks like we end up with a balance of $57.50. All right, we're moving into section 2.4, where we're going to start looking at change in a quantity and subtracting real numbers. So in the last section we were looking at addition involving signed numbers, and now we're going to look at subtraction involving signed numbers. And to subtract with signed numbers, we just use a little math trick, which is that we can rewrite any subtraction, a minus b, as an addition, a plus negative b. Or in words, to subtract a number, you can add its opposite. Now the reason we want to do this trick is so that way we don't have to learn new rules for how to use subtract when negative numbers are around. We're going to say what you do is you think of it as an addition problem, and then you just use those old rules. And we'll just show you an example here to show you that that works. If we have something simple like 7 minus 3, we know that's 4. We can do that subtraction because we don't think of it as involving signed numbers. But if we tried to apply this rule anyways, would it work? And the rule says take that subtraction and change it to adding the opposite. So instead of thinking of 7 minus positive 3, I'm thinking of this as 7 plus negative 3. And as we learned in the last section, when you have different signs, you take the difference, and the bigger number wins out on sign. So the difference is 4, and the bigger number is positive, so we still get 4. So when you look at that here, that might not look like such a good idea, because I took something simple that you learned how to do when you were in second grade and made it, complicated. But that's going to help us when we get to some of the messier expressions, like the negative 3 minus 9 or the negative 7 minus a negative 3. Of course, you're perfectly able to just go ahead and do this 7 minus 3 just like you always have learned to do it. But we want to remember that it could be done this way for the more complicated problems. So let's look at some of those examples. When you see negative 3 minus 9, what you want to do is rewrite the negative 3, and then the subtraction, you're going to say, nope, that's going to be an addition. And instead of subtracting 9, I'm going to add the opposite, so add it as negative 9. And now if we think of our rules on the number line, you're on the left and you move further to the left, both movements are to the left, we add those numbers up, we get 12, and if both movements are to the left, the answer is negative 12. And so, do you have to rewrite it? That's a question I often hear from students. And I would say, no, you don't have to, but here's kind of the test of whether you should or not. If I point at this number and say, what's that number? So think about that in your head right now. What is that number that I'm pointing at right now? So if your answer to that number was 9, then you're not thinking of this correctly. You should be thinking of it as a negative 9. So if I point at that number and say, what number is that? And in your mind, you think right away that's negative 9, then you could do this without rewriting it. You could just say, okay, I have a negative 3 and a negative 9. That's going to add up to negative 12. But if you think of it as a 9 that's being subtracted, then you want to rewrite this to force your brain to start thinking of all of these as addition problems and to see that as a negative number. And then on this next one, I would always rewrite this personally. When you have the two negatives, like I talked about in the last section, you have those two negatives, we're just going to make a positive out of that. So this is going to be negative 7 plus 3. Now that also fits our rule up here because it says if you have a subtraction, you can change that to addition, but then do the opposite of what this number was. And we know from, again, the previous section that the opposite of negative 3 is positive 3. And then when we look at this problem, sometimes people put negative 10 for that because they think of it like this, 7 plus 3. But we have to see those negatives as really kind of firmly attached to the number. So we're at negative 7 and then we go 3 units to the right. And what we really want to get out of that number line discussion is it's a left and a right. Those are opposite movements. And when you have opposite movements, you need to subtract. So I'm going to do 7 minus 3 there, which would be 4. But that's not the right answer because when you do this, you always have to think, well, what wins out? And it's the bigger number. And the bigger number was negative 7, so we're going to end up on the left. And so I'll put that negative in both spots, so it's actually negative 4. All right, let's finish off this page with an application. It says 4 hours ago the temperature was negative 12 degrees Fahrenheit, something we don't have to deal with in California too often. If the temperature has decreased by 19 degrees Fahrenheit in the last 4 hours, what is the current temperature? So you can almost think of this like a number line, which the thermometer kind of is, right? It's just a vertical one. On that thermometer, we were at negative 12. And then the temperature has decreased by 19. So when I hear decreased by 19, I think that sounds like a subtraction. It has gone down by, or we've subtracted 19 from what the temperature used to be. So what am I going to do with that? Well, again, how I do this depends on how you view this number. If you see that as 19, then you better rewrite it because it's really a negative 19. You want to see it that way. So I'm going to rewrite it. I have negative 12 and then plus negative 19. These are both positive, so I'm going to add them. Sorry, they're both the same sign. So I'm going to add them together. 19 plus 12 would be 11, carry the 1, 31. But they are both negative. So this is going to be negative 31. And then this one's an application, so we don't just stop at the number, we have to do the units, and it looks like the units on the temperature was Fahrenheit. So what is the current temperature? Negative 31 degrees Fahrenheit. Bitter, bitter cold. And again, some scratch work over there, so I'll circle my answer here. Alright, continuing on in section 2.4. The lowest elevation on dry land in the world is at the edge of the Dead Sea, negative 1,312 feet, and the highest elevation is at the top of Mount Everest, 29,035 feet. Find the change in elevation from the Dead Sea to Mount Everest. So the key word I think here is the word change. We're trying to find the change in elevation. When we're trying to find the change in quantity, we want to do a subtraction. In fact, we have that defined for us right down here. If you're doing the change in a quantity, then the change in the quantity is the ending amount minus the beginning amount. So it does turn into a subtraction when you're doing change. So find the change in elevation if you go from the Dead Sea to Mount Everest. So our ending point is Mount Everest, and Mount Everest is 29,030 feet high. So I'm going to start out with the ending amount, 29,035, and then I'm going to subtract the beginning amount, and this is where people get into trouble. What's the beginning amount? It's not 1312. The beginning amount is negative 1,312. So a lot of times people will do this as just 29,000 minus the 1,300 and not get the two negatives, but you have this negative and that negative for different reasons. This negative is because they want you to do change, so you have to subtract. And then this negative is because you're coming from an elevation that's below sea level. And if you have those two negatives, they're going to make a positive. So we do the addition over here on the side as scratch work. Actually, let's rewrite it. It's 29,035 plus, because of the two negatives, 1312. And now I'm going to do that scratch work. 7, 4, 3, 10, so 30. So it looks like the change in elevation would be 30,347 feet. And again, be really careful. One subtraction because of the word change, and then this negative because that was the ending, or the beginning elevation was itself negative. Alright, now we're going to finish up with a quick version of section 2.5, multiplying and dividing real numbers. So again, we're thinking about what happens when you have negatives involved. So, reminder from your pre-algebra class, if you have a negative times a negative, you get a positive, and then just do the multiplication of the numbers. So 3 times 6 is 18, and again, a negative times a negative is a positive, so that's why I'm going to say a positive 18. On part B, we have 35 divided by negative 5. Not absolutely necessary, but I will rewrite that as a fraction because that's how I tend to think of divisions in a math class. And this is a positive divided by a negative, so the answer is going to be negative, and then I'm just going to think about the math apart from that negative. 35 divided by 5 is 7, and again negative because it was a positive divided by a negative. Alright, and then moving on to the third one, we have a negative times a negative, so the answer is going to be positive. Just like up there. Doesn't matter that they're fractions, the same rule still applies. So a negative times a negative is going to be a positive. And then I just want to multiply 7/25 times 5 over 21. And when we do that, we want to think about what we can cancel. 7 and 5 are prime, so I'll just leave those in the numerator. But this 5 will go into that one, so I'll show the 25 as 5 times 5. That 7 will go into 21, so I'll show the 21 as 7 times 3. And then I've revealed what can be canceled. This 5 with one of the 5's in the bottom, this 7 with the only 7 in the bottom. And when we multiply the leftovers, there might be a temptation to say the answer is just 5 times 3, which is 15, and that is correct for the denominator. But if nothing is left in the numerator, we would still say there's a 1. If you think about what we're really doing here, we're dividing out of 5. So 5 goes into 5 once, 5 goes into 5 once. We usually don't write the 1 because there's other stuff left over. But when everything cancels out in the numerator denominator, we should think about the fact that there's still a 1 left in that spot. However, if the 1 is left in the denominator, you shouldn't write it because that's not considered simplified. All right, let's look at another one. Negative 5/7 divided by 15/8. So it's a negative divided by a positive. So that's going to work out negative. And then to divide fractions, you leave the first one alone, and then you multiply by the reciprocal of the second one. The answer is going to be negative. Thinking about common factors, the 5 goes into the 15. 8 is just made up of 2's, and there's no 2's in the bottom, so there's no need to factor the 8 and show those 2's. Copy the 7, break the 15 up into 5 times 3, so we can see that 5 that we can cancel. Cancel that 5, right, and multiply the leftovers, so we have that negative. I'm going to show that in the top, so negative 8 over 7 times 3, which is 21. It's actually a little strange for me to move that negative up to the top. I tend to like a negative out front more than in the numerator. But I did that just to point out this rule down here about signs. So you can have a negative in the top, a negative in the bottom, or a negative out front, and all of those mean the same thing. So they're all equivalent, and your answer should be considered okay if you have a negative in any of those places. Though generally this one we don't write so much. It's not wrong, but we're just not a fan. And the reason for that really is because you don't want to have negatives in your denominator. It just gives you more to think about when you're doing common denominators. But a negative out front or a negative out top, either of those is fine. All right, and then just finishing this off, they have a couple where they want us to use the calculator to work these out and then write our answer to 2 decimal places. So on problems like this, pure calculator problem, we just need to enter these in. So 64.958 divided by negative 3.716. I will point out on the calculator when I do the negative, I'm using this negative key right here as opposed to the subtraction key. And then I can just press enter and I get my answer. It said to round it to 2 decimal places, so I will do that and say that it is approximately, since I rounded, I'm bringing in some rounding error, 17.48. And on this one, there's a real temptation to say, okay, a negative times a negative is a positive, and start thinking about common factors, which is a lot of work, but they told you to use your calculator, so you should do that and just go ahead and round to 2 decimal places. We have a negative out front, which I use the negative key for. And then I have 169 divided by 175 times another negative 64 over 71, and then just round it to 2 decimal places, so that's approximately 0.87. I notice a lot of times people get thrown by these on my math lab because they try and work them out the whole way instead of just using the calculator as they're suggesting you to do. We're going to wrap this section up with just a little bit of a discussion on ratios. So write the ratio as a fraction. When they say the ratio of 6 to 8, that means 6 over 8 is the way we'll end up reading that. So 6 over 8. And then we simplify ratios just like fractions. So there's a 2 in both the top and the bottom. So I'll show that 2, cancel it, and we're left with 3 over 4. So that's the simplified ratio of 6 to 8. Now there's something they want us to think about in this section called a unit ratio, and that's a ratio where we write it as A over B or A to B, but the B has to be a 1. So I could do that with this one actually in a couple ways. I could write it as 3/4 over 1, or I could write it as 0.75 over 1, which is kind of the more common way to do it. Let me box this answer because that's the answer to that question, but it wasn't a unit ratio because the denominator was 4. When they start asking you for unit ratios, you have to force the denominator to be a 1. So let me show you how that works with this example. A person has credit card balances of negative $68.10 on a Visa and negative $29.50 on a Sears account. Find the unit ratio of the Visa balance to the Sears balance. So Visa to Sears means it's going to be Visa over Sears. So Visa, negative 68.10, over Sears, negative 29.50. Negative times a negative would be a positive. Negative divided by a negative would be a positive. So I'll just go ahead and get rid of those two negatives. And now you could spend a lot of time trying to reduce this and so on, but they want a unit ratio. So if it's going to be a unit ratio, they want the denominator to be 1. So I'm going to go to the calculator and I'm going to figure out what that division is. 68.10 divided by 29.50. They didn't give rounding directions here. It is money, so I'll just round it to 2 decimal places, 2.3. And then the second is a 0, but it's followed by an 8. Anything 5 or higher in the third place means we need to round up in that second place, so 2.31. I also think it's good to put units on it, so it's $2.31 over $1. And so that's a unit ratio now, because the denominator is a 1, and I got there just by doing the division on my calculator and writing that in the numerator and putting the 1 in the bottom. So what are unit ratios good for? There's a couple things. Let's see one of them by answering their question here, and then I'll mention another one. If the person wishes to pay off both accounts gradually in the same amount of time, describe how the result in Part A can guide the person in making his next payment. So what we want to do is think about the order here. The top was Visa, and the bottom was Sears. So for every $1 they pay on their Sears card, they'd want to pay $2.31 to the Visa if the goal was to pay them off gradually at the same time. So I always like to do my interpretations from the bottom up, and keeping in mind it's Sears on the bottom, Visa on the top. So for every $1 the person sends to the Sears account, they should send $2.31 to Visa. Now, we're definitely not recommending here that the person just send $1 to Sears and $2.31 to Visa. We're saying for every $1 they send to Sears, send $2.31 to Visa. But they should probably send a lot more to Sears if they can, right? Let's say they decided to pay off $57 to Sears. So 57 going to Sears. What should they send to Visa? Well, for every one of these, they should send 2.31. Well, there were 57 of those, so it would be 57 times 2.31, or $131.67. I just made up the 57, but the point is, whatever they send to Sears, they should send 2.31 times that much to Visa. So one of the things that a unit ratio gives us is a multiplier. That number in the numerator, 2.31, tells us what to multiply our Sears payment by to get our Visa payment. And that idea of thinking of a unit ratio as a multiplier is going to become very important much later on in the course. All right, that wraps up section 2.5.